In this video, I'm going to take you through a variety of different calculations involving a variety of different equations. The purpose being to establish this connection between an equilibrium involving water and equilibriums involving acids and bases. And so we're going to talk about water, we're going to talk about the hydronium ion, hydroxide ion, and we're going to talk about pH and pOH. So why don't we get started? So if I look at this particular reaction between water, I would be able to label it into Bronsted-Lowry, and I'd be able to label my water as an acid and as a base. And so we really hopefully appreciate that if water is acting as an acid proton donor, it's going to lose that proton and it becomes a conjugate base. If water acting as a base then accepts that proton, it becomes a conjugate acid. And so what I do establish here is an acid-base equilibrium involving hydronium ion H3O+ and a hydroxide ion. And so if that is an equilibrium, it's going to have a K expression, and that K expression looks like this. It's called Kw, so that's the water dissociation constant, Kw, and it actually has a value of 1.0 times 10 to the minus 14. So if I was to solve that, to find out concentrations at equilibrium, I'd let that equal x, and I would solve for x, and x equals 1.0 times 10 to the minus 7 equals, at equilibrium, at SATP, the hydronium ion concentration and the hydroxide ion concentration. And so that's why pure water at SATP is considered neutral, because the concentration of these two ions that give rise to acidic or basic solutions is equal. But it's that interplay between equilibriums, the changes in hydronium ion versus hydroxide ion concentrations, that give rise to differing pHs. And so that's what we're going to start investigating now. So first of all, given that Kw expression, we can solve a simple little question. What is the hydronium ion concentration of sample lake water with a hydroxide ion concentration of 4 times 10 to the minus 9 moles per liter? Is the lake acidic, basic, or neutral? So we just learned this Kw expression. Kw equals concentration of hydronium times the concentration of hydroxide. We want to find the concentration of hydronium, so hydronium concentration equals Kw divided by hydroxide. And so we just substitute in our values. 1 times 10 to the minus 14 divided by hydroxide ion concentration 4.0 times 10 to the minus 9, and we get a hydronium concentration of 2.5 times 10 to the minus 6 moles per liter. So that's the hydronium ion concentration. And is the lake acidic, basic, or neutral? Well, the lake is acidic because H3O+ concentration is greater than that neutral 1 times 10 to the minus 7 moles per liter concentration. So if it's greater than neutrality, it means it's more acidic. So that lake is actually acidic. All right, so that's the first expression you want to kind of appreciate. That's the Kw expression. Okay, so let's move on to pH. Now, you have, I'm sure, seen this equation, and so there is, by definition, the pH. pH is quite literally defined as the negative log of the hydronium ion concentration. And so that's another equation you need to try to come to terms with. And just to remind you, the pH scale, so a pH scale goes from basically 0 up to 14, where at the low end of the scale we have strongly acidic solutions. So a pH of 1 is actually a hydrogen ion concentration of 0.1 mole per liter. Every pH unit we decrease the concentration of hydronium by a factor of 10. So pH of 2 is tenfold less concentrated, pH of 3, 0.001 moles per liter, and at neutrality it is 1 times 10 to the minus 7 moles per liter. So the difference between a pH of 1 and a pH of 7 is a millionfold difference in hydrogen ion concentration. So we change hydrogen ion concentration very quickly as we move up the scale. Obviously, the high end of the scale, it's very weakly acidic, which means it's very strongly basic. So the concentration of hydrogen ion at the high end of the scale is going to be very low. The other useful equation is the calculation of hydronium ion given a pH. So hydronium ion concentration equals the negative log of pH, or 10 to the negative pH, and that gives you a concentration of moles per liter. So let's use this information. We can do a quick little calculation. Calculate hydroxide ion concentration of a solution of baking soda with a pH of 8.5. So we're given the pH. So we want to find hydroxide ion concentration. So we're going to have to first find hydronium ion concentration. So as I just said, hydronium ion concentration equals 10 to the negative pH. So that's 10 to the negative 8.5. And we would plug that into our calculator and come up with a concentration, hydronium ion concentration of 3.16 times 10 to the minus 9 moles per liter. And then we want to find hydroxide ion concentration from hydronium. So hydroxide ion concentration equals Kw divided by hydronium ion. And therefore the hydroxide ion concentration is 3.16 times 10 to the negative 6 moles per liter. So two simple little calculations allow you to convert from a pH of a solution to its hydroxide ion concentration. And again, obviously, in terms of looking at where the solution lies on the pH scale, pH of 8.5 means this is actually a basic solution. And that is borne out by the fact that the hydroxide ion concentration is greater than hydronium. So it's not at neutrality, and because hydroxide is greater than hydronium, it's basic. All right. Carrying on. Well, we have a pH scale. Stands to reason that someone came up with a pOH scale. So pOH scale is fundamentally the same, but with the frame of reference is now hydroxide ion concentration. And so something that is strongly basic will have a low pOH. So this implies a high concentration of hydroxide ion concentration. At the other end of the scale, something that's strongly acidic will have a high pOH. And consequently, we have equations that allow us to determine the pOH and the hydroxide ion concentration. So they're no different than the calculations involving hydronium ion. And there is one more equation I want to show you, and this is this nice little relationship between pH and pOH. So pH plus pOH equals 14. The proof of that comes from the rules for logarithms, and I'm not going to go into that. If you're interested, you can look that up. But this is a nice equation. If you're given the pH, you can very quickly find pOH by manipulation. And so we're going to do a couple questions to show that to finish off. So here's the question: what is the hydroxide ion concentration of a solution with a pH of 3.8? And I want to show you two different ways you can solve this. So the first route is we're going to find hydronium ion concentration first, and then from there we find hydroxide. Okay, so how do we find hydronium given pH? Well, we've already done that. So HCO plus concentration equals 10 to the minus pH equals 10 to the minus 3.8 equals 1.58 times 10 to the minus 4 moles per liter. And again, pH is pretty low. That's quite acidic. That's a pretty high concentration of hydronium ion. Second step to find OH, which we've already done as well, is Kw divided by hydronium. And so 1 times 10 to the minus 14 divided by 1.58 times 10 to the minus 4 And when we do that, we get a hydroxide ion concentration of 6.31 times 10 to the negative 11 moles per liter. And once again, that should make some sense to you because the pH is low. That means it's acidic, which means the concentration of hydroxide ion should be low. And so it all makes sense when you look at the numbers and that relation between hydroxide and hydronium at neutrality. So that's one way we determine hydronium and then hydroxide. Well, there's the second way. And in this case, we're going to find the pOH, and then we're going to find hydroxide ion. So our question remains the same. We're just approaching it from a slightly different point of view. So if you remember, 14 equals pOH plus pH. So the pOH equals 14 minus pH, which equals 14 minus 3.8, which equals 10.2. So pOH is 10.2, and then hydroxide ion concentration equals 10 to the minus pOH, so the negative log. So that's 10 to the minus 10.2. And we get a hydroxide ion concentration, not surprisingly, of 6.31 times 10 to the negative 11 moles per liter. So we do get the same answer, which is nice. We should get the same answer. We are calculating the same thing. We've just done it from two different points of view. So those are the sorts of equations you need to be able to carry out. And the equations you have at your disposal are shown here. These are all the different equations you can use to manipulate your given variables. And that concludes this video.